We're in part 3 now, and we're about to learn how signaling works in the membrane of the neuron, okay, the individual neural cell. It turns out to be the same way it happens in the muscle cell, so you're going to be learning sort of a 2-for-1 here. 2-for-1, 1-for-2, I can't remember. One thing you're going to be learning can be applied to two things. Okay, so basically we're learning this idea here. I'm solving for voltage in this equation. I'm sort of redefining things here a little bit. They're solving for current, which is current equals voltage divided by resistance. But I think this is an easier equation. And I love physics and electricity and all that kind of stuff. And so I go for this one. Here's when things flow. This is current. This is resistance to flow. Okay, so we're going to have a resistance to current. That's the R. The voltage is what happens when we have resistance. So let me explain you, as my Chinese professors used to say in Chinese medicine. I explain you this. So check this out. I'm holding this surgical scissors here at a distance above the surface of the book. Okay, and this is potential. And the reason I know it's potential is that if I let go of it, I have action. Okay, so action is when something happens and things move through the universe. Potential is when things don't happen, but they could because there is a force working upon it. What is the force working upon the scissors? It is 9.8 times 9.8 meters per second squared. It's a change in velocity from 0 to acceleration. Okay, so basically there is a force acting on this called gravity. Okay, and acceleratory force, it'll get faster and faster up to a certain terminal velocity. Unless you're in a vacuum, then there's, terminal velocities don't count quite so much. So at any rate, the idea here is that I'm going to have potential. And another word for voltage is potential. So that's a good thing for you to consider. What is the potential? The potential is the amount of current, how much can things move, times resistance. Okay, so that's the potential. If I had a much larger object here, first of all, the possibility for movement would be greater, and I would have to use a lot more strength to resist dropping it. Right, so the resistance would also be greater, and it would be a huge voltage. Okay, this is a very small voltage with the little tiny scissors like that. So I can measure the volts over here. It's actually in millivolts, and the average membrane of a neuron is going to be about minus 70 millivolts. That's what you need to know. Okay, and I should have drawn a graph in here, but I think the graphs in your textbook are adequate for this purpose. So we're going to be looking at resting potential, and I'm going to compare it with the active potential or action potential. This is the way it's normally expressed. And so I have a membrane. I just drew this membrane. If we were in the classroom, you would watch me draw little circles. Whenever you see me drawing these little circles like this with little tails coming off the circles, these would be actually sort of like triglycerides, only it's a diglyceride. It's only 2 fatty acids coming down from a head. And instead of the third fatty acid, I've spun that carbon around and I've added a phosphate to it. So I have 2 fatty acids in each case. And in the third carbon, which would have been the triglyceride, I have it pointed in a different direction and I have a phosphate head on it. Okay, now the fatty acid tails are fat, right? And they're nonpolar, and so they don't mix with water. Almost everything that's happening here is happening in water, so I need you to understand that. Okay, and so that means the phosphate head is going to mix well with the water. Water is polar. It has a partial charge to it, and so it's a very polar type of molecule. And this has a definite charge on it, not partial, but very definite, and so it mixes with water. These charges do not have to do with the phosphate. The phosphate actually has negative charges. So don't worry about that. These are molecules which I'll explain are moving toward. We have positively charged ions and negatively charged ions. These are mostly proteins down here. So we'll get to that. Anyways, this is outside the membrane this direction. This is inside the membrane this direction. If you happen to have a lot of omega-3 in your diet, then you would have these fabulous fatty acid tails here, which are going to have omega-3. Okay, a lot of people don't have that. You could have that. Okay, so consider it. You have the handout for it. So ask for it if you don't have it or you can't find it anymore, because it's got a list of foods on it, and it's also got a list of information about what disease states are remedied by adjusting your omega-3. Okay, moving right along, we do have two channels here. We have a channel for sodium and a channel for potassium, and that's because over here we have a standard issue sodium-potassium pump, just the way you like it. It's a active transport pump right here, just the way you like it. It's got a little ATP-driven motor on it, and it's pumping sodium out of the cell. It's pumping potassium in. All cells do this for a living. It's not unique to neurons or to skeletal muscle or any other. It's actually something that's commonly found. The interior, the cytoplasm of all cells, is rich in potassium, and outside the cells, the extracellular fluid is rich in sodium, and that's just the way it is. These do a little bit more work in that direction because they need to create electromotive force. Okay, so that's what we're going to do, is we're going to create an electromotive force, EMF, and we're going to ultimately, initially, we're going to create a potential here. What is the potential? I have sodium out here, and my sodium channel is closed. I'm showing the sodium bouncing off of the closed channel. Over here I have potassium, because we can exchange a positively charged ion for another positively charged ion, and the system stays balanced. In here the potassium comes over. It mostly bounces off its sodium potassium channel, but some of it leaks through. That's an exquisitely important detail, and the detail will change next semester when we get to heart action potentials. So the heart is a much more complicated system, and this is quite simple by comparison to what's going on in the heart. So stand by, as it were. We'll get into that. Meanwhile, we have a little bit of leakage here, which means we have a slight fall of parity, and we have a little bit more positive on the outside than we do on the inside. As a result of the positive charge on the inside, there are proteins which are going to drift up here and create a negative charge over here. Now, I want you to be aware that this is a membrane. Okay, and I want you to think of the scale. If this is the membrane, and this is the inside here of the, how shall I say, the neuron, some part of the neuron, the part that's going to be having action potentials. Any part of the neuron can have action potentials. But let's imagine that we're either in the axon or we're in the cell body. Where is the membrane, like on the other side? If this is the axon, it's about 20 stories away. It's a long ways away. This is a very local event. I want you to think of it as a local event, although it's going to move. Once we get action in this system, we have to go, for instance, from the toe, if I'm feeling the temperature of the water in the pool, all the way to my spinal cord. And up my spinal cord, a single neuron will bring that at a speed of somewhere in the vicinity of 100 meters per second. So things are going to move, seriously move, 100 meters per second. Okay, which means there's a lot of activity going on here at a fast speed. And this is all local. Okay, I need you to understand that. What we have here, because the channels are closed, is potential. Okay, as long as I hold the scissors above the table here, nothing's happening, right? And it's not until I drop the scissors that something actually begins to happen. Now, if I had a whole row of dominoes, and I push the first domino, and you can get a whole bunch of stuff to happen if you have your dominoes arranged correctly. And so that's what's happening here is we have a lot of dominoes that are perfectly arranged in order for something very lengthy to happen at a really nice speed. So, okay, here's our resting potential. Nothing's happening. We're at rest. I have not disturbed the system. I have not stimulated the system. And let's take a look now. They actually have here their own voltmeter, and their voltmeter is showing minus 70 volts. Do you see it there? Okay, and then we can go on over here. Now we can get little blips. Here they actually have a nice graph. They're showing us the resting potential at minus 70. Okay, so we're going to pick up the action next.